In grading your quiz these days, I found some of you are not catch the point of our course. Therefore, before starting the material today, I will review some important concepts at the beginning. So, Rn is our Euclidean space. Rn. The element in Rn is x. The point is x. X has n component x1, xn, and for two elements in Rn, for xy in Rn, the inner product or scalar product is xy to be the sum of the multiplication of their components. Okay, this is the product, inner product, and the norm is the square root of the inner product of x which itself. In the textbook, the norm is denoted by double bars, but to simplify the notation, we will use the pair of single bars to denote norms. Of course, if you prefer the double bar notation, it is also okay. The single bar is justified because if n equal 1, then this is the same as the absolute value. Therefore, we use the single bar even for higher dimensions. This is justified by the special case n equal to 1. So having defined the inner product, we introduce the distance between 2 points. If x and y are 2 points in Rn, their distance is the norm of their difference. This is the difference, this distance. And if r is a positive number, then BRA, A is a point in Rn, then BRA is the ball, consists of all points in Rn whose distance to A is less than r. Okay, so this is geometrically, this is the ball centering at A and the radius r. This is the BRA. We also call this the R neighborhood of A. R neighborhood of A. This is a very useful concept. For example, a set S is bounded. We said a subset S of Rn is bounded if S is contained in some ball. Those balls which radius at the origin, we simply omit the center A. That is the origin, simply denoted by BR. BR is BR0. Okay, so using the ball, we can define the boundedness of a subset. Boundedness. Now we consider sequence in Rn. Sequence in Rn, xk is a sequence in Rn. We said xk converges to a point A. What this means? This means this is a sequence of points in Rn. The distance of every point to a fixed point A converges to 0. So this means the distance from xk to A. This is a sequence of real numbers. This sequence of real numbers converges to 0. If this sequence of real numbers converges to 0, we say the xk converges to A. Okay. So this is quite intuitive. And we also prove that xk converges to A if and only if every component of xk, that is, we denote xk by xk1, xkn. Every component of xk converges to the corresponding component of A. Okay, so this is an important result. So using the balls we just introduced, we also have some important topological concept. Suppose A is a subset of Rn, and we said A is an interior point of A. We use the A, which is a small circle here, to denote the set of all interior points of A. Therefore, a small a belongs to this set 0 means that small a is an interior point. What this means? This means that there is an R positive such that BRA is a subset of A. This means that not only A in A, capital A, all points near this A, because this is our A. So the R neighborhood of this point is this set, this ball. That is the point A and all points near A also contained in the set A. So this is the meaning of interior point. The point not only belongs to A, the point around this point also belongs to A. Then this point A is an interior point. Okay. And then we also need an important concept, the limit set. Limit set denoted by A prime. What's A prime? A prime consists of all the limit point of A. All limit point of the set A. Then what is a limit point? A is a limit point. A is a limit point means A is an element of A prime. Okay? This means there exists a sequence containing in A but not equal to A, such that this sequence converges to the point A. Okay? If a point can be approached by a sequence in A, then this point is a limit point. And we require this sequence to not equal to A. Why we need this section? Why we need this? Because, for example, if this is A is this region and a single point here, this point A also belongs to A. So we don't want to call this separate A here a limit point, because we could not have other point approach. We could not have other points in the set A approaching this small a here. It is a separate, isolated point. We don't want to call such an A limit point. Therefore, we restrict our requirement for the approaching sequence. Every term should not equal A. Okay, so this is why we need this condition. So limit point. This is equivalent to say that for any epsilon positive, the intersection of the epsilon neighborhood of A, which is the set of A, but removing the point small a, is not empty. So A is a limit point, is equivalent to this property. The small a, every neighborhood of the small a contains point in capital A other than the small a itself. Okay, so all this we have proved in our previous lecture. We just review here. Okay, limit point is very important to define the limit. We will see this later. Okay. Now we consider functions. So a variable function is a map f from a subset of Rn to the real numbers. Here, capital A is a subset of Rn. This means for any given x in A, because A is a subset of Rn, therefore all pointers in A has n component. So this x can be denoted by x1, xn. For every x in A, you are assigned a real number. A real number is assigned to this x. Of course, for different x in the set A, the real number is different. So this real number depends on x. Depends on x, so we denote this by fx. This real number denoted by fx. So this is the value of the function f at the point x. Okay, so of course, because x has n components, so you write fx means x is a point in Rn. But if you want to emphasize that f is an unvaluable function, you need to write fx as fx1 xn. Okay, in the first left-hand side, the x is a point in Rn. It is a point, but the point has n coordinates. In the right-hand side, the x1, xn are real numbers. So this is why we call such a function unvaluable function, because it has real numbers as variables. Okay, so this is a scalar function or real valued function, because the function value is in R, is in the real number set, therefore is in R. We can also consider the vector valued function. That is our main object of study in this part, differential calculus for nonlinear mapping. Vector valued function. What's this? This is a map f from A, also from a subset of Rn, said A, but the value is not in R, but in another Euclidean space Rm. Okay, so this means for any x in A, you are associated with a point y, but y is in the codomain Rm. You have a y in Rm associated with this x. Of course, this y depends on x. For different x, you have different y. So this y is denoted by fx. So this is a vector valued function. Both x and y are elements in Euclidean space. X in Rm. X in Rn. Actually, x in A, a subset of Rn. Well, y in Rm, another Euclidean space. So this function we denote in this very compact form, very brief, very simple. But if you want to write in coordinate wise, component wise, this is exactly this. For every x, x1, xm associated to y have xn associated to y has m component y1, ym. So every y1, ym, the coordinates of y1, ym are all dependent on x1, xn. Therefore, they are all functions of x. So if you let fi from A to R. What's fi? Fi, we require fix to be the yi. Okay. Then this gives us a real valued function fi. For every I from 1 to n, we have this real valued function fi. So so this yi. So our map f from A to Rn is equivalent x1, xn maps to y is y1, ym, but every y1, yn are functions of x. So y1 is f1x, y2 is f2x, ym is fmx. If you write x in component wise, this is f1, x1, xn, fm, x1, xn. So this is a vector valued function. Okay. So every yi are functions of x1, xn. This is true for I from 1 to n. So the vector valued function, our vector valued function f is equivalently f is determined by all these f1, fn, m. So f we denote by f1, fm. So we use this notation. Use this notation in the last line to mean that the components of f is f1, fn, fm. Okay. So this is vector valued function.